All right. Good morning, everyone. Welcome to today's webcast. I'm Tony Truelove. I am the Global Marketing Communications Manager for Eaton, and I will be your host today for the webcast. And the topic will be low NOx regulation compliance with an exhaust burner. And we've got some great content today, but before we get started, I wanted to do a little housekeeping. And basically, feel free to interact with the presenters at any time, ask questions in the question box down below. So type them in, hit send. We will get to as many of those as we can in today's allotted time frame. The slides will advance automatically throughout the event, so you don't have to worry about advancing the slides. If you're having trouble, you can go ahead and type your message into the Q&A box. We'll try to help those that we can, but I would say if you're having connectivity issues, if you can't hear us or see us, the best thing is to probably log out, log back in, and you should be able to be right back to where you started. All of the materials that we're going to cover today, including the slides, are available in a couple of different widget folders that we have at the in the console. So you will see an SAE Mobilis widget, and that's where all of the SAE papers are. And then the slides for today and the two other papers are in a separate widget folder. And then finally, this event will be archived. Feel free to view it on demand. Share this with any colleagues who might be interested in this. We'd be glad to have you guys take a look at this at your leisure in the future. So with that, I wanted to introduce you to our presenters today, Dr. Tom Harris and Dr. Jim McCarthy. Tom Harris is a senior technical specialist at Tenneco, and he has over 20 years of industrial experience in after-treatment component and system design and development. In 2016, he joined Tenneco, where he focuses on the future after-treatment and thermal management solutions for commercial trucks and off-highway equipment. Dr. Jim McCarthy is a senior chief engineer for New Spaces Innovation within the Eaton Vehicle Group and is an SAE fellow. He has focused his engineering career on conserving fossil fuels and reducing emissions by creating organic growth solutions through innovation, product development, intellectual property, and publications for the best powertrain solution of engine and electrification. And before we get started today, I wanted to do a little survey. And this survey is to really kind of gain a little bit more insight about where your company is in its NOx and CO2 emissions reduction strategy. So take a second here and respond to the survey with the appropriate answer. And this will probably help us guide some of the questions and answers that we get from you guys. So take a look at that. Okay. So let's see where we are. Okay. Give you just a minute here, give a few more of you the opportunity to respond to the survey. All right, here we go. Okay. So I just shared the survey results with you guys. Looks like several of you are still considering what your emissions reduction solutions are a couple of years away. That's good. I think you'll find the discussion today very beneficial. So let's go back to the slides. And speaking of the presentation, so today's discussion is really about the fact that regulations are driving the need for innovative solutions. We're all facing a simultaneous reduction in NOx and CO2. And Tom and Jim have authored 4 journal papers, and they're going to share the collaborative testing results on fuel burner technology alone and on solutions when paired with other technologies. So with that, I'm going to turn it over to Jim, and he's going to kick it off for us.
Thanks, Tony. Appreciate you putting this session together, and I'm super excited to be presenting with Tom Harris. We've been working really closely together for the last 2 years, yet we've known each other and worked on other projects before this endeavor, but this is a special endeavor. So from an introduction standpoint, we're looking at 2027 with lower emissions and improved fuel economy. Now, the California Air Resource Board has issued their standard, and the EPA is close to introducing theirs, but it'll be, for CARB at least, the Composite Federal Test Procedure, which is the heavy-duty FTP, is set to reduce NOx down to 0.02 grams per horsepower hour, which is a 90% reduction from today, and adding a new cycle focused on low load. Typically, under these low load cycles, the NOx is around 1 to 1.5 grams per horsepower hour, and we're dropping down to 0.05, which is more than a 90% reduction. As we look at how to improve NOx, we need to realize that high NOx conversion really starts when the SCR, the selective catalytic reduction catalyst, is above about 250 degrees C. And as shown on this plot, we're showing that when we get above 250 C, we're in that peak efficiency zone where we can reduce most of the NOx. Whereas if we're too cold, we have subpar NOx reduction. So there are some enabling tools and pairings of tools that we can use together to go ahead and improve that temperature and improve NOx. One of them is cylinder deactivation, where we can deactivate half the engine. We could deactivate 2 cylinders, 4 cylinders, and we have a full authority control over cylinder deactivation. And what that does is it lowers the air-fuel ratio. And when we lower the air-fuel ratio, the exhaust temperature goes up. And that goes ahead and produces more heat for the after-treatment system. At the same time, it improves our fuel efficiency because the engine's more efficient running on these lesser number of cylinders at low load operation. We can also go ahead and do a dual SCR system. And as pictured here, we have a light-off SCR, which is upstream of a conventional after-treatment system consisting of a DOC, DPF, SCR, and ammonia slip. And this light-off SCR is about 4 feet downstream of the turbocharger and is about half the size of the downstream SCR. So it's not a small system, but it can be real close to the engine, which can be heated up really quick from the exhaust stream. And also the focus of today is really highlighting the benefits of a fuel burner. And we place the fuel burner upstream of a DPF and an SCR. And really the focus of today is to show everybody what the burner can do by itself and when paired with a dual SCR or a cylinder deactivation system. So this really was a joint development where Tom and I were able to work together, and we partnered with Southwest Research. Our first publication was the heavy-duty FTP, which we began in March of last year and presented in December. And then we went ahead and did other cycles in March of this year. The first one was an ATZ presentation, which Tom presented, and the second one was an SAE presentation, which I presented this past April. Tenneco also did another endeavor where they looked at simulation and testing of the fuel burner. They began this in October of last year, and Tom presented this at the April SAE World Congress meeting. Following that meeting, Tom went ahead and presented at the GAMC VEEE conference, where he went ahead and showed more results, and he'll talk about that when that section comes up. Then we combined all efforts. We combined the fuel burner with a light-off SCR with cylinder deactivation, and we published this in the Frontiers in Mechanical Engineering Journal. We began this in May of this year. We finished in July, and it is currently waiting for publication. And once that becomes published, we'll have Tony Truelove put that on the website so that you can access that testing result as well. So with that, I'd like to hand it off to Tom Harris. Tom?
Thank you, Jim. I'd like to start by highlighting that the exhaust burner is actually a system, not just a single component. And in particular, part of this system is a air pump or blower that provides air for combusting the fuel in the burner. On the right-hand side of this figure, you see the type of blower that Eaton is providing to the partnership that Tenneco and Eaton have on providing this exhaust burner system to medium and heavy-duty applications. The Eaton device is a Roots type blower. It's powered by an electric motor with a power supply of either 12 or 24 volts. The burner device on the left-hand side, you can see, is integrated with the exhaust pipe. The fuel and air are brought in together in what we call the back wall, and then they pass through an atomizing nozzle, which creates the fuel and air spray, which is then ignited by an ignition device. So with that background, we can start getting into the test results. And again, as Jim mentioned, we're going to start by describing the testing that was done at Southwest Research Institute, jointly funded by Tenneco and Eaton in 2021. And I'm going to focus on the results from the FTP test cycle. Those results were presented at the ATZ Heavy Duty Engine Conference last December. And I'll note that the other authors on this paper include Chris Sharp, Brian Zavala, and Andrew Mateus from Southwest. The test bed is described on this slide. The engine was a Cummins 15-liter, 500 horsepower engine in the production state and running production software. This is going to be in contrast to later on in the webinar, where Jim's going to describe some testing where with a similar Cummins engine, but one that has been upfitted and calibrated for cylinder deactivation. But importantly, for the first part of this webinar, the results are coming from a production engine running production software. The aftertreatment system is shown on the right-hand side. It happened to be part of a system that was provided to Southwest Research Institute as part of the CAR blow-NOx demonstration. You can see that it includes a DOC DPF, SCR, and ammonia slip catalyst. This is a single dosing system. And the substrate dimensions are and volumes are listed down below. The catalyst technology in this system would be representative of model year 21 production catalysts. The burner shown in the middle figure or picture is was close coupled to the turbocharger outlet, and then there was about a 1 meter length of pipe connecting the outlet of the burner to the aftertreatment system. In most of the tests, that pipe was not insulated, but in a couple of results that you'll see in the following slides, we did apply insulation. Lastly, the system was hydrothermally aged to an equivalent of 435,000 miles. This is the current full useful life definition, but in future regulations, this would be referred or will be referred to as the intermediate useful life, and the full useful life will be quite a bit longer than this duration. Now we'll go on to the test results. Again, we're focusing on the FTP test, which this is for the heavy duty version of the FTP test. And as most of you are aware, it is a single cycle that is run first after the engine has cold soaked overnight. Then the engine is turned off for 20 minutes, and then the cycle is repeated. That second part is called the hot start cycle. And the results from both of those cycles are combined in a weighted average calculation to give what's called the composite tailpipe NOx result, which is shown in the far right-hand column there. And in the table, we're describing 4 individual tests. The first one represents the baseline. The burner was not operating during the test. You can see the composite engine out NOx there is less than 3 grams per horsepower hour. This is consistent with an engine that uses exhaust gas recirculation, of course. And then the tailpipe value in the right-hand column is 0.14, which is consistent with the engine calibration and this after treatment being able to meet the requirements, the current limit in the EPA and CARB regulations of 0.2 grams per brake horsepower hour. The three other rows in the table represent tests that in which the burner was operating, and one of the key parameters that we found was important in this testing was a control feature of the burner that is basically an on-off switch. It's associated with the DPF out temperature, and the purpose of it is really to manage the trade-off between providing heat to convert NOx versus burning excess fuel and just contributing to more CO2. So that switch is really the major knob to adjust to manage that trade-off. In the second row there, we did a test with a single valued threshold of 200 degrees Celsius applied to that switch. And you can see in the tailpipe results that this reduced the NOx by about 70%, but we're still well above the target of 0.02 grams per horsepower hour. We then tried a slightly different variation on this control scheme where we used what we called a two-tier threshold for the on-off switch. The upper threshold, or the first threshold, was 300 degrees Celsius, and then later it was reset to 200 degrees Celsius. I'll provide some more information on this in a minute that will help clarify that, I think. This two-tier threshold ended up having quite a positive impact on the tailpipe NOx, reducing it, cutting it in another half, basically. And in the final result, you see at the bottom of the table, we applied insulation to the pipe section in between the burner and the after treatment system and achieved the lowest value in the study of 0.023. So we're not quite meeting the target, but we came pretty close. And again, let's recognize here that we're using a production engine with production calibration. So the overall system was certainly not optimized. Now we see on the right-hand side a plot. This corresponds to exhaust temperatures measured during the first 600 seconds or the first half of the cold start FTP, corresponding to the results in the last row of the table on the left-hand side. The gray curve in this plot is the threshold value. So again, I mentioned in that test we were running a two-tier threshold. The threshold started out at 300 degrees Celsius, and with that higher value, the burner stays on longer. The burner being on is indicated by the red curve, the DOCN curve being elevated up toward 500 degrees Celsius. Now, as I mentioned, this threshold is tied, or rather the on-off switch is tied to the DPF outlet temperature. That's the green curve. And so you can see when it rises up to reach 300 degrees Celsius, not only does the burner turn off, as indicated by the red curve dropping, but also the threshold value is reset to 200 degrees, and it's maintained at that value for the remainder of the test. You can see that as a result, or with that 200 degree lower threshold, the burner does turn back on one more time between 500 and 600 seconds, but after that in the FTP cycle, it remains off. So what we learned from applying this two-tier threshold control strategy is that it allows us to decouple really two independent or separate functions of the burner. Obviously, the one function is to heat up the after treatment system as quickly as possible during the cold start. And a higher threshold value helps in that regard by allowing the burner to stay on longer so that a thorough heating can be achieved. However, once that objective has been reached, you're really more in what we call the keep warm mode. And a lower threshold value is much more appropriate in terms of balancing NOx conversion versus additional fuel consumed by the burner. Now, that issue of fuel consumed by the burner is addressed on the next slide. It's perfectly reasonable to assume that the burner operating leads to higher CO2 results. But I think you'll find that that doesn't have to be the case, and in fact wasn't the case in our testing. First, on the left-hand side, we see now CO2 results for the same 4 tests that were described on the previous slide. And if you notice, the baseline test provided 506 grams per horsepower hour. The final test run that gave us the lowest NOx result actually ended up with a slightly lower CO2. We'll call this CO2 neutrality just to be fair, but this is maybe a surprising result to everybody, but I think it's easily explained, and to help explain it, I've used the illustration on the right-hand side. This is suggesting or illustrating how the engine is behaving during the cold start FTP test, going from left to right. So the baseline test is described at the top of the illustration there. The production engine is doing its thing according to its production calibration. For a cold start, it starts out in thermal management mode, where more fuel is being burned so that more heat can be provided to the exhaust. As it happens in the Cummins, with the Cummins engine and this after treatment system, you go about halfway through the cold start FTP cycle before the engine transitions out of thermal management mode into fuel economy mode. That transition is triggered by a downstream after treatment system meeting some threshold value. So now if we look to the bottom of the figure, when the burner is also operating, it basically causes the engine to trigger that transition from thermal management to fuel economy mode to occur much sooner in the cold start. And as a result, all of that extra time now that the engine is running in fuel economy mode, it's producing less CO2 relatively. And it just happened that in that final test at the bottom of the table there, the amount of extra CO2 produced by the burner almost exactly matched the reduction in CO2 coming from the engine. So hopefully you find that explanation satisfying. And again, I'll just remind everybody that this testing was done without any modification of the engine calibration. Presumably this trend could even be pushed in a more favorable direction with regard to CO2. So now I'm going to turn the microphone back over to Jim, who's going to describe the low load cycle testing that we also did as part of this testing at Southwest in 2021.
Thanks, Tom. I will say that, as Tom and I and the Southwest team were working through that, we were trying to figure out why this doesn't work. And really, after a couple months, we came up with that 2-tier strategy, which Tom showed that, hey, that really works. It dropped the NOx in another half and helped us with CO2. And I'll start with that, saying that we use the same the 2-tier strategy on these other cycles presented here at WCX this past April. And this was authored with the same participants: Andrew Mateus, Brian Zavala, Chris Sharp, and of course, Tom Harris. So I'll start off by saying that we did have an optimization approach. And as we look at these cycles, there's a low load cycle, which is shown on the left. It's a 1.5 hour test cycle, and the engine speed shown on the top and the torque shown on the bottom. Now, the average load of this cycle is very low. It's only 6.1%, but it's a 1.5 hour cycle. So I was working with some results, and I was talking with Chris Sharp a long time ago. I needed to go to Brazil, and I needed a cycle that represented Brazil driving. And we came up with this US beverage cycle, which is actually a portion of the low load cycle. The nice thing about the beverage cycle, it's only 800 seconds long. The average load is a little bit lower than the low load cycle at 4.7%. So what we did here is we did our optimization on the beverage cycle because we could run a lot of beverage cycles in a day, whereas on the low load cycle, it was very time consuming. So we did our optimization on the beverage cycle being 800 seconds long, and then applied that learning and ran the low load cycles later on in the test program. And this was a very efficient way that we found to go ahead and conquer the control strategies for these other cycles. From a control strategy standpoint, and Tom talked about this, our initial tests were focused on heating up the SCR as quickly as possible. And this helped early in the cycle, but we needed optimization. And that's where this two-tier strategy came in. We weren't getting the results that we desired, that we thought we should have. So we really raised that first tier strategy to go ahead and get that temperature up to about 300 C quickly. And then we lowered it back down for really maintenance mode. Once everything's hot, we can go ahead and shut off the burner and only turn it back on when we need to, as opposed to cycling it on and off. And our feedback SCR temperatures are very similar to what Tom showed. For these low load cycles, we kept the same first tier at 300 C, and then we investigated, okay, what would 180, 190, and 200 C do for our test results, and we'll share those with you in this section. And then really our strategy was using the enthalpy from the burner, which is about 53 kilowatts, really for this get hot scenario. Get hot as quickly as possible, and then cycle it on and off for what we would call a stay hot scenario. So let's start with one of my favorite cycles, the beverage cycle. And it's one of my favorites because it's a low load cycle and it's only 800 seconds long. And on the left, I'm showing the base after treatment. This is the same production cal that Tom talked about. The engine out NOx was about 4 gram NOx, and it drops to about 2.1 on this beverage cycle. Now, the beverage cycle is not a regulated cycle. It's a portion of the low load cycle, but this is what we use for our optimization. When we went right to the two-tier strategy, starting at 300 C and dropping down to 200, the engine out NOx went up to about 5.9 or 6 gram NOx. But you can see here that the tailpipe NOx is near zero. It's 0.001. So an outstanding result by adding a burner to a conventional aftertreatment system. And what I'll direct you to the graph on the right, and we'll start with the SCR inlet temperature. This two-tier strategy is shown in the blue, whereas the baseline system is shown in the black. So the baseline engine without the burner, which is a production setup, really ranges between 150 and 170 degrees. And as you might recall from the introduction, we really want to be above 250 C. Well, with the burner added to the conventional aftertreatment system, our average increase was on the order of 64 degrees, which is significant, such that the SCR was somewhere in the 180 to 260 range. And as a result, that was able to go ahead and drop that NOx down to near zero at 0.001. Now, if we look at the middle graph on the right, which is NOx reduction, the baseline system shown in black, which shows a variation of 20 to 100% NOx reduction, depending on the cycle over the beverage cycle. And when we add the burner to it, we're at near 100%. Now, I forgot to mention on the graph on the right, it shows 0 to 1600 seconds. This is 2 consecutive beverage cycles. So the beverage cycle is 800 seconds, but we go ahead and run 2 of those just so that we can go ahead and capture the full effect. Then on the bottom, we show when does the burner turn on. So the first y-axis shows the burner energy in kilowatts, which cycles between, let's say, 15 and 36 kilowatts. And you can see that it's turning on around 100 seconds and shutting off just slightly after 200. It stays off for a while, comes back on around 450 seconds, so on and so forth. And if you're wondering how much energy that consumes, the second y-axis shows the cumulative burner energy in kilowatt hours, and it's about 5 kilowatt hours. So that's what our two-tier strategy did for SCR temperature, NOx reduction, coming up with about 5 kilowatt hours of energy. Now, if we went ahead and looked at a single tier strategy, let's call it 190 degrees C, we dropped from a 5.3 NOx down to a 0.007, which is also a good result, but not as good as 0.001. But what I really want to emphasize is when we drop down to 180 C, we're now seeing that exponential increase in tailpipe NOx up to about 0.09. So really, you don't want to go as low as 180. 190 is probably okay, but we went ahead and kept it consistent with the heavy-duty FTP results that Tom shared, kept the same control strategies, so that's easy for someone to implement, keep the same two-tier strategy for the FTP and all the other cycles. And that's an easy way to go and producing excellent results. So let's move over to the low load cycle. We did all of our development optimization on the beverage cycle, and then we ran the low load cycle with the same type of results. So our baseline system on the low load cycle went from about 4 gram NOx to about 0.9. When we implemented the two-tier strategy, starting at 300 degrees, dropping down to 200, we went from a 4.6 gram NOx to 0.006. So 0.006, that's an excellent result. The standard moving forward in 2027 by CARB is 0.05. So we're a magnitude below that. So this is a great result. And if you want to see the SCR inlet temperatures on the right, we can go ahead and see that the baseline system shown in black, that's somewhere between 120 and 240 degrees Celsius. When we add the burner to it, we're showing an increase of about 60 degrees, and that takes us between 180 and 300 degrees C. If you see the NOx reduction graph on the right in the middle, we see the black is the production system, and the blue is nearly 100% all the time with some excursions slightly lower, but an excellent set of results. And then if you were wondering, how long does the burner stay on? It's the bottom graph. We're showing the full 1.5 hour cycle. The dark blue line is the burner energy, which cycles between about 15 and just about 50 kilowatt hours, 50 kilowatts in this case. And you can see it cycling on and off for a cumulative burner energy of about 15 kilowatt hours over this low load 1.5 hour cycle. I'd also like to point out that a two-tier strategy of 300 and 190 C, so 10 degrees lower on the stay hot scenario, also produces excellent results down to 0.008. But similar to the beverage cycle, we don't want to go to 180 because then we see that increase. So we're seeing excellent results with the two-tier strategy of 300, 200, which is completely consistent with what Tom showed on the heavy-duty FTP. Or if we want to drop it down to a 190, we're also getting excellent results. So the key takeaways for this burner upstream of a conventional after-treatment system is on the beverage cycle, we're showing near zero NOx. It's 0.001 grams per horsepower hour, which is a great result. As a result, we're seeing a 13.4% increase in CO2, but once again, we did prove that near zero is possible. On the low load cycle, we're also showing near zero at 0.006 for an increase of 9%. Once again, we're showing near zero is possible. And then for our stay hot cycle, this is in the paper, but I'm not going to go ahead and emphasize this. This is we're running down the road on a vehicle and we drop to idle for an extended period of time. And we can go ahead and maintain the SCR temperature at the temperature needed for 99.9% NOx reduction, corresponding to near zero NOx. And this corresponds to an increase in CO2 by about 10.9%. But near zero was achieved. Having said that, I'd like to pass the baton back over to Tom.
Well, thank you, Jim. So in this next section, this represents work that was conducted at Tenneco, both testing and simulation, following up on the results from the testing at Southwest Research Institute, which we have just described. The testing results, which focused on using the burner for preheating the after-treatment system, was carried out at Tenneco. So the other co-authors that you see there, Raphael Ballard, Matt Mulick, and Gunter Palmer, are also Tenneco employees. And then in addition to presenting those results, also we did some simulation work that was combined in the presentation at the VEEE conference that is shown down below there. So I'll cover all of that in this next section, although very briefly. So the motivation for this follow-up work, both in this section, also the last section that Jim's going to describe, is really the recognition that the results that we achieved in the 2021 testing at Southwest didn't quite meet the finish line. And so we wanted to get across the finish line, basically with this additional work. Specifically, with regard to the FTP, the issue was that we hadn't quite reached the target of 0.02. And of course, we need to even go below that to provide NOx engineering margin. And the root of the problem here is really clearly seen in the cumulative NOx results that I have shown on the upper figure on the right-hand side. This is for the cold start portion of the cycle in that best NOx result, composite NOx result that I spoke to earlier. You can see that after 200 seconds, the tailpipe NOx increases only a little bit. So effectively, the SCR system is 100% efficient from that point on. On the other hand, almost all of the NOx is emitted in the first 100 seconds. So any solution that we might propose here really needs to focus on that portion of the cold start, the very beginning portion. So I've listed here 4 opportunities for providing NOx engineering margin. The first one is one that we wished we'd had time to explore in the testing at Southwest, and that is to recalibrate the engine's thermal management mode to reduce the engine out NOx. That's the red curve here, which of course would also lead to reducing the tailpipe NOx. Another option is to use the burner to preheat the aftertreatment system, and I'll speak to that on the next slide. A third option is to bring the SCR function onto the DPF, that is to substitute a SCR on filter or SCRF component there. And then the last option is to perhaps consider adding a light-off SCR catalyst to the aftertreatment system and or cylinder deactivation to the engine. And we actually were able to do this experimentally, and Jim's going to speak to that in the fourth section of the presentation. Now, with regard to the low load cycle or low load operation in general, clearly Jim showed that we could get to very low NOx levels, but there was a price to pay in terms of CO2 being produced by the burner. So the challenge here is to operate the burner in a more efficient manner, or to do something else, such as adding cylinder deactivation to the engine. And again, Jim's going to speak to that last item later in the presentation. But I've also investigated some burner control strategies that might improve the CO2 as well. So in this, in the study of preheating with the aftertreatment system, this testing was done at Tenneco, not at Southwest Research Institute. It did use exactly the same burner prototype system that we had used in the testing at Southwest, but the engine was a 13-liter on-highway engine that, and also the aftertreatment system was a little bit smaller than the one used at Southwest because of this smaller displacement engine. The one other thing to note here is that the engine intentionally was run the entire time in fuel economy mode. So what you see down below are results from running a cold FTP test, but the engine was not running thermal management mode at the beginning of that test. And this is reflected in the left-hand plot. The blue curve corresponds to the baseline or burner off test. And you can see the temperatures there are quite low during the first 600 seconds of the FTP cycle. The other two data sets in this plot are tests where the burner was operated both for preheating and was operated when the engine was running. Again, the DOC-in temperature being elevated is a good indication of when the burner is on versus off. All three of these data sets, by the way, were time aligned to the start of the engine, and that's reflected by the dashed gray line that you see in the plot. Now, the two tests in where the preheating was taking place with the burner, you can see that the temperature rises quickly to around 500 degrees Celsius. In one of the tests, we did preheating for 5 minutes, in the other tests for 3 minutes. That's the green curve. And in both of those tests, you can see that the temperature tops out at around 500 degrees and oscillates there. This is another control feature of the burner that is designed to protect the DOC from getting too hot. And in the end, actually, we realize that this is the real limitation to what you can accomplish, or the real limiter to what you can accomplish with preheating. That being said, we also recognized in this testing that if you were able to provide more airflow, that you could actually operate the burner at higher power and put more heat into the after-treatment system while respecting that 500 degree temperature limitation. So to do this from a convenience perspective in the testing, we simply applied a second Eaton air pump, fed in the air from it upstream of the burner. So this effectively doubled or more so actually, more than doubled the total airflow through the system during preheating. Then once the engine was started, the second air pump was turned off, and only the amount of air needed from the first air pump was going to support the combustion in the burner. By the way, I should have also mentioned that in this study, for the preheating, we're operating the burner under lean conditions to minimize the emissions. These would be off-cycle emissions of hydrocarbon, CO, and NOx. They all ended up being quite low under those combustion conditions, and the details are provided in the paper. The other two things that we learned from this study are illustrated in the right-hand plot, which is now the DPF out temperatures for the 3 tests that I described earlier on the left side, and then one additional test where the burner was used for preheating, but then was not operated during once the engine was started. That's the yellow curve, and the other colors for the curves are the same as on the left-hand figure. So the first thing you can notice in this plot on the right-hand side is that the DPF out temperature doesn't increase, or did not increase, in any of the 3 tests where preheating was carried out. And this tells us, of course, that the DOC and DPF are acting like heat sponges, basically absorbing all of that heat and operating the burner at 25 kilowatts, and even for 5 minutes is not enough to completely saturate that sponge, basically. So you might think this is a little disappointing if the idea is to heat up the whole after treatment system, but in reality, it doesn't matter so much, because what you can see is once we start the engine, so to the right of the dashed gray line, the heat is swept from the DOC and DPF by the exhaust coming from the engine, swept from the DOC and DPF into the mixer and SCR. So in fact, the SCR does get heated up quite rapidly as a result of the preheating. And you can see from the case where only preheating was done, the yellow curve, that this initial pulse of temperature is definitely the result of the preheating. So we learned a lot about preheating from a thermal perspective, or temperature perspective, in this study, but unfortunately, when we looked at the NOx results, we realized that our SCR catalyst had been degraded by some earlier testing, and really the NOx results, which would have been nice to correlate with the temperature data that you see here, wasn't really going to afford that comparison. So what I did instead is I went back to the data from the Southwest Research Institute testing, created from that a GT Power model with all of the same sizes of substrates. The model was calibrated to the temperature data from that testing, and then also with the dosing rate data and NOx emission data, we were able to calibrate the catalyst performance in the model. So with that GT Power model, then I was able to correlate the temperature behavior that you see here with reduced NOx emissions. In fact, even with a preheating period less than 3 minutes, we saw the tailpipe NOx being reduced below the 0.02 gram target, and providing some engineering margin. And this is, the details are described in that VEEE presentation. Now, the other thing that the model allowed us to do was to consider alternative burner control strategies for low load operation, and in particular the low load cycle. So what I'm showing here are simulation results. First, on the left-hand side, you see the DPF out temperature, and the green curve corresponds to the controls that were used in the Southwest testing. Again, the on-off behavior of the burner is basically being carried out by or controlled by a switch that's tied to the DPF out temperature, and a particular threshold can be applied to that switch. So with that control strategy, which Jim referred to as being optimized in the testing, but I would say we optimize that control strategy, but it might not be the optimal control strategy. You can see the oscillations in the temperature, the green curve there, just exactly what was seen in the test results that Jim presented earlier. Now, the blue data that you see in that plot comes from a completely different control strategy. I call it a heat tank control strategy, where we are using the burner to control the heat stored in just the DOC. So the control element includes a hysteresis element with an upper and lower threshold for heat levels in the DOC. And as it happened, the two threshold that I chose for the simulation that gave the blue results there was able, as you can see, to maintain the temperature very close to 200 degrees Celsius when the exhaust temperature is less than that. And then at around 3,000 seconds, and also at around after 5,000 seconds there, you can see the exhaust temperature is higher. This is actually due to what's coming out of the engine, and the burner is actually off during that part of the cycle. So with this alternative control strategy, we are definitely able to minimize the temperature swings in the system, or reduce those temperature waves passing through the system. But what we really care about is, did this affect how much fuel the burner was consuming? And this is spoken to on the right-hand figure. The x-axis is the burner consumed by the burner fuel consumed, and the left-hand axis is the cumulative tailpipe NOx. The green data points, now they represent two different simulations using the original controls and varying the lower threshold of the two-tier threshold strategy that Jim and I have spoken about earlier. And as you vary that lower threshold, of course, you're basically defining the beginnings of the trade-off curve between NOx and fuel consumed by the burner. The blue data points there represent the new control strategy. I'm getting different data points by varying the lower threshold for heat stored in the DOC. And you can again see that it generates a trade-off curve, but the key thing to notice is that trade-off curve is shifted by 35% in terms of the fuel consumed by the burner. So here's just one example of an alternative way of controlling the burner that actually does lead to much less fuel being consumed by the burner, much less CO2 being produced by it during these low load operations. So with that, I'm going to turn the microphone back over to Jim, who's going to describe the last bit of testing that was done as part of this overall program. Jim?
Thanks, Tom. Well, that's some exciting work. So as we looked at this work together, we did a lot of optimization. And what we wanted to do was go ahead and combine other elements such as cylinder deactivation and a light-off SCR. But I will note that as we did this, we only did this for about 5 days of testing, but we were not able to add in that latest burner control strategy that Tom talked about, showing that impressive 35% fuel savings. So As I show these results, there's more to come in the future for future optimization. So what I wanted to talk about is adding more levers. So in the first set of work, we took a production engine, we added a burner with a conventional after-treatment system, which we talked about previously in this webinar. These new configurations, we add a cylinder deactivation engine, upstream of the burner, and a conventional system, and then we added a light-off SCR. So I'll talk about these two new configurations. So I broke these into technology levers, and I'll first start with the composite FTP, where both NOx and CO2 are regulated. And if we look at our single lever, that's a 50 kilowatt burner with a production engine, where Tom already shared with you that we were able to achieve 0.023 grams per horsepower hour at carbon neutrality. We're saving 0.7% CO2 with that. If we combine CDA in the second row with the burner, and this time we're going to toggle between a maximum of 50 kilowatts on the cold cycle, and during all the other cycles, like the hotter cycles, we'll max it at 20 kilowatts. We were able to show that we get to 0.02. Now, we did 1 day of testing. We had to combine a lot of results because we really didn't have the time and budget to do much more than this. So we were able to do that at about a 1.5% CO2 increase. But future optimization, especially with what Tom was talking about with the new burner strategy, I believe that could get that down much lower on CO2, but perhaps the NOx challenge is still there of getting too much below 0.02. But combining CDA with the light-off SCR and the burner strategy, we were able to get to 0.012. I will note that that's 1 day of testing. Future optimization is possible. We showed 0.9% increase in CO2. I truly believe that getting that to CO neutrality and perhaps a 1% savings is very achievable. So with 2 levers, we dropped the FTP NOx to 0.02, and with 3 levers, we showed 40% FTP margin down to 0.012 at close to CO2 neutrality. Let's move to the low load cycle where NOx is regulated, and I'm showing the same format. With 1 lever, we showed 0.008 on the low load cycle. That's a great near zero NOx limit, but that cost us 11% CO2, and this was done back in 2021. And we've obviously progressed the technology since then. If we add CDA to that, we're also getting a great NOx level of 0.011, so more than 75% NOx reduction to the 0.05 standard, and it costs us 6.9% CO2. But as you see, we went from 11% to 6.9, then that's a direct contribution of CDA lowering that CO2 impact. Now, if we add 3 levers, the CDA, the light off, and the burner, were between 0.006 and 0.021, so more than 50% margin up to more than 80%, and we're showing between 3 and 0.2% CO2 increase. But as I mentioned, that was 1 day of testing. We could go ahead and improve that, especially with the encouraging results that Tom talked about with the new burner control strategy. So with 2 levers, we showed 75% margin and cut the CO2 penalty in half. And with 3 levers, we showed 60% margin with close to CO2 neutrality. So let's look at our key takeaways. So we presented 5 pieces of work, 4 journal papers, and a conference presentation. And if we look at the first one, the heavy-duty FTP, Tom really did show the simplest system with the production engine where you're only adding a burner. We showed a composite NOx of 0.023 with CO2 neutrality. So we want to get NOx down a little bit lower, but in very, very encouraging results. Then we went to the low load cycles where we showed the low load cycle, the beverage cycle, and the stay hot cycle, showing that we had near zero NOx on all these cycles. So near zero NOx is achievable. The third piece of work, we showed the burner preheat, which enabled lower cold start NOx and the control strategy for reduced CO2 under sustained low load conditions. And remember, Tom was able to show a path to reducing that CO2 or that fuel by 35%. And then we're presenting at Frontiers in Mechanical Engineering, our 4th publication, where we combine CDA, light off, and the fuel burner we demonstrated 40% margin for NOx on the heavy-duty FTP with close to CO2 neutrality, and we demonstrated 60% NOx margin on the low load cycle. So I'll just hit on some conclusions. We have multiple options for meeting 2027 carb emissions, and these have been demonstrated. Meeting NOx and remaining CO2 neutrality or better is key to moving forward, and it is achievable. Adding a CDA, light off, and fuel burner is a complete system that meets NOx while remaining CO2 neutrality. And meeting the 0.02 composite NOx on the FTP and 0.05 has been demonstrated more than 5 years in advance of the CARB 2027 mandate. With that, back to you, Tony.
Thanks, Jim. Thanks, Tom. Lots of really good information. You guys have generated a ton of questions. We have just about 5 minutes left in today's presentation, so we're going to try to get to as many questions as possible. So if I could ask you guys to keep your responses as brief as you can. So let's start off with Tom, one with you, for you here. So what is the ideal location for the fuel burner, upstream or downstream of the PDF? I'm sorry, a DPF.
Yeah, we would like to see it placed in upstream of the DPF, both because it's nice to have an additional substrate there for buffering the temperature or serving as a heat reservoir, as I described earlier. And then also the DPF is there to pick up any particulates that the burner might produce, although it doesn't produce particulates in general.
Okay. Tom, maybe here's another one for you. What changes were made to the fuel burner system that made this so successful on this testing versus the one that maybe you guys did a couple of years ago?
Yeah, that's a really good question. I think this probably refers back to the early stage of the CARB low NOx demonstration where Southwest was testing a Tenneco burner. But that particular burner had a nozzle in it that only allowed it to provide a maximum power, heating power of 25 kilowatts. And as you saw in the presentation here, the testing in 2021 at Southwest that we did was with a 53 kilowatt nominal burner.
Okay. Not sure who wants this one, but what flow rate is the burner capable of, and what is the max flow rate used during preheating? You talked a bit about preheating.
Gosh, I don't have the number off the top of my head, but this is something clearly within the capability of the Eaton Roots blower that was employed in the testing, well within the capability.
So
right.
Tom, on that, the Roots blower for preheating, we can do about 74 kilograms per hour. When we added the two pumps together, we were up around 150 kilograms per hour, and the majority of the flow is going to come from that air pump, and we'll add a little bit of fuel to it as well.
Right. Thanks, Jim.
Okay. Here's a good one. Are there various size options if the requirements don't require the full 56 kilowatt capability?
I'll say on the Tenneco side, yes, we have different designs for the burner, one of which is sized for a small passenger car application, and then a couple in between that one and the heavy duty burner that was tested at Southwest. Okay.
Here should be an easy one. What fuel is being used for the burner? You showed diesel. A diagram earlier. Diesel fuel, right?
Diesel fuel. Yeah. Same tank as the engine.
Okay, excellent. Let's see, a couple of more here. DEF consumption. What did you see an increase in DEF consumption during any of this testing?
Nothing that was that noticeable in the results from the testing at Southwest.
Okay. Jim, you talked about levers. Can you just quickly recap the number of levers that you think are going to be required in order to achieve the future emissions?
Yeah, so adding a burner is one lever that gets us really close, and depending on the regulation, you may want to add a second lever. We're adding cylinder deactivation helps with that heat stream and reduces CO2. And adding the third lever of a light-off SCR really brings it all together and produces substantial margin. And we showed 40% margin on the FTP and 60% margin on the low load cycle.
Okay, that's about all the time we have for today. I do appreciate your attention for the full hour. Hope everyone learned a bit of information. And as I said, all of the documentation and the papers that Jim and Tom presented are available for download. If you do have more questions or would like more information on our exhaust thermal management solutions, you can scan that QR code, takes you to a page on eaton.com, and you can very easily get to the fuel burner or to some of our other technologies. And with that, I do appreciate your attention. Thank you very much and have a great day.